Hi, my name is Jim, and this is an introduction to electric circuits. And what we're going to use is a water example to explain some of the key concepts, which is very, very common. But before we get into that, we need to cover some very basic introductory criteria that will be used throughout the electronic sequence. And one is the concept of voltage, and voltage is basically a pressure, like water pressure. And the symbol for voltage is V, and I might say that the voltage of a lithium-ion cell is approximately 3.7 volts. So here's a device with a lithium-ion cell, and if there are more than one cell, it's called a battery. And I'm going to refer to one or more cells as batteries from now on. Now when I flip that switch, what we had is a current flow out of the negative terminal of the battery through a light emitting diode, through a limiting resistor, and then back into the battery, in addition to powering up the rest of this circuit, which basically does some unique things with audio. So we also have the rate of electron flow is called current, and a 60-watt light bulb, and this would be an incandescent light, not an LED or a CFL, I would be equal to approximately 0.5 amperes, and A is the term for amperes, it's the symbol, and whenever you're dealing with a decimal point, it's always good to put a leading zero. So the reason we do that is because numbers typically don't start with a leading zero, so if that is, say, an artifact of a copy machine noise or whatever, we might mistake 5 amperes for 0.5 amperes. So it's good practice to always put a leading zero if you have a decimal point. Resistance is what we call the opposition to electron flow, and we might say that the filament of a 60-watt light bulb, which is made from tungsten, which is the metal with the highest melting point, is 240 ohms. So in this case we have R equals 240, and the symbol for this is the Greek letter omega, and that represents ohms. And then finally what we have is power, and power is the rate that energy is converted. And in the case of a 60-watt light bulb, we could say that 60 watts would be 60 what's called joules, and a joule is a watt times a second. And in a 60-watt light, we say that 60 watt seconds are converted from electrical energy into heat and light. And unfortunately, in case of an incandescent light, about 5% of that is light, and the remaining 95% is heat. Hence the migration to CFLs and light-emitting diodes. They're very efficient. So our electric meter measures energy, and they don't care what we convert it into. Could be heat for an electric water tank, or light bulbs, of course, or whatever, but that's what we actually purchase from the electric company as energy. And the joule is a very small unit, so the electric company's meter is rated in kilowatt hours, but that's what they sell us, and that's what we pay for. So that's some of the basic backgrounds of where we're going here. These concepts are very important. Pressure, voltage, current flow, and resistance, and finally power. So if we go to explain this using a water example, what we have here is a water tank there, and we see the water level, a little fish in there to tell us that it's full of water. And since this tank sits above ground, gravity attracts the water, and that produces a pressure. Now, batteries have pressure too, even though no current is flowing. A water tank with no water flowing also has pressure, and think of a hose where the spigot is turned on, but the nozzle is turned off. There's water pressure in the hose, but yet no water is flowing. Now, if we open the spigot, the amount of water that comes out of that is going to be turned by the resistance that the spigot and the pipe offer to the flow of water. And let us say, for example, over perhaps a 2-hour period, that we end up with the amount of flow of water that produces 10 gallons of water on the ground. Now the electrical similarity to that would be the Coulomb, and that would be the number of electrons. And this is not a rate of flow, it's just the number of electrons. And that is approximately equal to 6.242 times 10 to the 18th electrons, abbreviated as 6.242 e to the 18th. So these electrons would be sitting here on the ground per se, as represented by our 10 gallons of water. Now, in science museums, you may have noticed that they have devices on pedestals with a great large metal ball on top, and when these are lit up, they produce sparks. So what's occurring there is electrons are gathering on the inside of the metal ball, and since it's a conductor, it's also on the outside, and it reaches a certain potential that can ionize air and produce a mini lightning strike. The electrons in this case come from a rubber belt, which is rubbing on a conductive brush, we'll say, and the friction of that causes triboelectric effect, which causes electrons to accumulate on this metal ball. So we don't use coulombs much in electronics, but what we do use an awful lot of is current flow. So current flow I is equal to the rate that electrons flow past a point in a circuit per second. Now we're going to look at a little circuit, later. Just to make the point clear here, suppose that I open this spigot and we have a flow of water coming out. The rate of the gallons per second would be equivalent to current flow. So 1 coulomb per second is equal to 1 ampere. Now the resistance of the spigot, that's the on-off valve in a hose if you will, determines the rate at which water comes out of it. Likewise, in an electric circuit, the resistance of the circuit determines how much current flows. Now the pipe also offers resistance to current flow, so if I open the spigot 100%, I would get a flow of water coming out of this in gallons per minute, gallons per hour. What's important is that it's a rate of flow. Also note that if I had a larger pipe, suppose this was 1/2 inch and I replaced it with a 1-inch pipe, and the spigot would be adapted to 1 inch, the flow rate would be much larger. And that is because a larger pipe, and think of cross-sectional area in this case, is larger than that of a 1/2 inch pipe, hence the resistance to the flow of water is less and more water flows. So that kind of illustrates the water concept as related to an electric circuit here, and we're assuming in this case that the water level is going to remain constant, because in fact as the water level drops, the pressure also drops, and that would be the case, say, in a battery where the chemical energy that's stored is depleted, and hence it's not able to deliver as much current or power as it could be when it was at full charge. So we also have the concept of current as expressed in an equation here, as the current I is equal to the charge Q divided by the time T. So for example, if I had 1 coulomb of electrons passing a given point in the circuit, and it only took 0.1 second to do it, 1/10 of a second, that would mean that 10 amperes of current were to flow for that 1/10 of a second. Likewise, we have symbols for pressure in an electric circuit, and this is the symbol for a power source or a battery. The larger line here represents the positive side of the battery, and the smaller line represents the negative side of the battery. And as I said before, this stores chemical energy, and what we can see here is an excess of electrons, but they can't flow around unless there's a completed circuit path. So all batteries have an electrostatic potential even though no current is flowing. Now the symbol for resistance is this squiggly line here. Its unit is ohms, and that symbol is omega, as I stated before. So let's take a look here at an actual circuit. And we're going to be introducing Ohm's law here, which is very fundamental. It's imperative that you know this without question by heart every time, without doubt, because you're going to be using it like forever. And the equation is that the pressure voltage is equal to current flow I times the resistance R. Now, here I have a circuit with a pressure source. It's a 120 volt battery in this case, if you will. A resistance is shown as a 60 watt light bulb where the filament would be made from tungsten, and the area of the tungsten wire and the length of it and the characteristics of tungsten determine the resistance of this. I've kind of drawn a little circle around it to indicate that it is evacuated, so the heat doesn't interact with oxygen and actually burn the light bulb up. And here I have a switch, which when it's closed, I'm going to have a completed circuit. So electrons in this case, indicated by E negative, are going to flow out of the negative terminal battery through the light bulb, and when they go through that resistance, they lose energy, and that energy is converted into heat and light. They go through the switch and re-enter the battery at the positive terminal. So what we can say about that is we have electron flow from the negative terminal of a battery to the positive terminal. Now, unfortunately, many years ago, a mistake was made in an experiment, and the scientists thought that current actually flowed out of the positive terminal of a battery through a circuit to the negative terminal. So as opposed to electron flow, this direction is called conventional flow. And as fate would have it, the industry adapted conventional flow. Now about 95% of colleges uses conventional current flow and 5% uses electron flow. I learned on electron flow, but converting to conventional flow is very easy. Even though the physical current is flowing from negative to positive, conventionally we speak of current flowing from positive to negative. Now that may be a bit confusing, but when you hear it enough, you just take it for granted, and in the back of your mind, if you want to think about electrons, then they flow in the opposite direction. But it's really not necessary to do that. The industry is very comfortable with conventional current flow. So getting into Ohm's law here is what we have is the pressure V is equal to current flow I times the resistance R. And therefore, if we did a little algebra on this, we could say that the resistance R in ohms would be equal to the voltage divided by the current, which in the example of our 60 watt light bulb would be 120 volts divided by 0.5 amperes. So the resistance for the filament of a 60 watt light bulb would be 240 ohms. Now I'm telling you a little bit of a lie here. That 240 ohms occurs when the filament's hot. Tungsten is very nonlinear resistance relative to temperature characteristics, and the input surge to this can offer a current flow of approximately 6 times 0.5 amperes. And that's why a lot of times the light bulbs burn out when you turn them on. It's that surge of current that causes them to fail. Further, the filament is eroded on the sides, but we won't get into that right now. Likewise, if we wiggle this around a little bit, let me see here, we'll talk about the current flow equal to the voltage over resistance. So 120 ohms divided by the hot filament resistance of 240 ohms equals 0.5 amperes. And then we could also say, of course, that V equals I times R, which equals 0.5 amperes times 240 ohms equals 120 volts. Now, an easy way to remember this is kind of a pie chart where we have V, I, and R. So we cover up the guy we want. So, for example, if I want current flow, I can see that it's V divided by R. If I want to find out what the resistance is, it's V divided by I, and conversely, if I want to find the voltage, it's I times R. So that's kind of helpful. Also, we have the concept of power, and the fundamental equation for that is P equals V times I. In this case, 120 volts times 0.5 amperes would give us our 60 watts. And likewise, we can solve for different variables in this. The current would be equal to the power of the voltage, which would be 0.5 amperes, and the voltage would be equal to the power divided by the current, which would be 120 volts. Now, a shortcut to remember power is the same kind of thing. We have P, V, and I. So we cover up what we want to find. If we want to find the voltage, it's equal to P divided by I, and so forth, as indicated by the previous example. Now, going a little bit further with this, and we do some substitutions, what we know is P equals V times I, and we also know that V equals I times R. So if we substitute in I times R for V, we have P equals I times R, which was our V, times I, which equals I squared R. And if we were to wiggle this around a little bit differently, we would also find that the power is equal to the voltage squared divided by the resistance. So we have three general forms of power equations, P equals V times I, P equals I squared R, and P equals V squared over R. And all three of these are going to be used many times in different applications. If you're given, say, the current and the resistance, there's no sense in computing the voltage when you can use them directly to find the power in a circuit. So that'll conclude on our introductory component of electric circuits, and then we'll move on and talk about what's the difference between a conductor and an insulator. And just for reference, all these lines here are conductors. When the switch was open, before I closed it, the air in between the switch contacts was an insulator, and that's exactly what happens in your home when a light fixture is turned off. So with that, I'll conclude, and thank you for watching.